Okay, good morning. Oh, that was really sad. Try that again. Good morning. Great, excellent. I hope you had a good break. We have a week of classes, new lessons left, and then the next week, we'll spend next week doing final exam review. So we have, including this one, 3 more lessons to go over. Now, if you look at this projector here, I don't know how to get rid of that stupid warning there. I'll try to write around it. I can't see it here, but I'll try to write around it. If it gets in the way, let me know, okay? Okay, so we're going to look at section 10.3. Continuing with our investigation of polar coordinates. All right, so today we're going to focus on sketching polar graphs. Before we can do that, let's do a quick review of how to put a point down in polar coordinate. Okay, so remember, we specify a point by giving a value theta and also a value r. So for example, the point 2, comma, pi over 3. So what you do is you start with the angle, go to pi over 3, which is right here. Right? And then if r is positive, so this determines what quadrant you start in. This is in first quadrant. If r is positive, you stay in the same quadrant. So you go 2 units forward into that quadrant. Positive r, you stay in the same quadrant. If r is less than 0, then you go to the opposite quadrant. So for example, we do negative 2, comma, pi over 3. Then once again, we use the angle to tell us where we are to start. So here's my pi over 3. Puts me in the first quadrant, but a negative r means I go into the opposite quadrant. So I go over here. Right? I start here. Positive r puts me in the first quadrant. Negative r, I go backwards, puts me in the third quadrant. All right, remember this stuff? Yep? Okay, now we need to be comfortable with this thing before we can sketch equations given in polar coordinates. So this is a very, very important concept. All right, so now let's sketch something. Let's sketch a simple one here. R is equal to cosine theta. And we'll do this the old-fashioned way. We'll choose a bunch of values of theta. Find the corresponding r, and then connect the dots. And because we know trig functions are periodic, what to choose in terms of theta is actually very easy to determine. So here, cosine of theta has a period of, what's the period of cosine? 2 pi, right? Yeah. So that means if I can find what r is doing for the first 2 pi of theta, I know what's going to happen afterwards. This is all I need to take care of. Right? So I choose theta. And then I find r, then I connect my dots, and then I have my shape. All right? So let's see. 0 is a good place to go. Pi over 4. I'm going to choose values that I know what I can do with cosine easily. Pi over 3, pi over 6, pi over 4, this kind of thing. Pi over 2, 3 pi over 4. Let's see, 5 pi over 4, 3 pi over 2, 7 pi over 4. Oop, I got room. And 2 pi. Here we go. Okay? Then we find out what r is equal to at these cosine values. So cosine of 0 is 1. Cosine of pi over 2, pi over 4, sorry. Right. Which is roughly 0.7. So for the purpose of sketching, I'll just truncate it after the first decimal. Cosine of pi over 2. Come on, you know this stuff. 0. Good. Let's continue. This one is, so that's roughly negative 0.7. Cosine of pi is minus 1. 5 pi over 4 is negative again. 3 pi over 2, 0. 7 pi over 4, positive root 2 over 2, roughly 0.7. Cosine 2 pi is 1. Okay? Now it's going to repeat after 2 pi because we know the period of cosine. So after 2 pi, it's going to go back to here again, right? So 2 pi and 0 are the same. So the next one after that is this, so on, so on, so on, and so on. Right? Okay, so let's see what we get here, what this shape looks like. And I chose the theta values to go in increments of pi over 4. So to help me sketch these things, I'm going to put these 2 dashed dotted lines here because these are pi over 4s. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, blah, 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 right? So those are sketching guides. They kind of tell me where to go. Okay? Now let's put down our first point, 0, 1. This is saying theta equal to 0, right here. And r is equal to 1. So I go over here, 1 unit. Let's say right here. Right? So let me label these things. So this is point 1. Point number 1. point number 2. At pi over 4, I go 0.7. This is pi over 4. So let's kind of eyeball 0.7 right here, more or less. So that's point number 2. Pi over 2, y-axis. I want to go 0 away from the origin. So right here, right? So that's point number 3. So far, so good? Yeah? Let's keep going. 3 pi over 4. 1 pi over 4, 2 pi over 4, 3 pi over 4, right here. 3 pi over 4 puts me in the second quadrant, but my negative r kicks me into the fourth quadrant. Remember that? So it's negative 0.7, which is right here. So this is my point number 4. And then pi minus 1, that's point number 5. Pi is right here, this direction. Positive r, I go in that direction. Negative r, I go backwards. So where is point number 5? On top of point number 5, right? See that? 1 and 5 are the same thing. Okay? Point number 6. 5 pi over 4. 1, 2, 3, 4, 5. So this takes me to third quadrant. But then a negative r kicks me into the first quadrant. So do you see that this is the same as point number 2? Right? How about point 7? Where does it go? 3 pi over 2 is right here. I want a 0 r, so I sit on top of 3. And notice this continues. 7 pi over 4 is right here. My point 8. 7 pi over 4 puts me in the fourth quadrant. A positive r makes me stay in the fourth quadrant. So this is the same as point number 4. And finally, 2 pi and then 1. So this is number 9. 2 pi is right here. 1 point. So right here. Okay, see how we got these dots? 9 of them. Questions? Okay, now let's connect the dots. 1, 2, 3. So let's go this way. If you want to know what's between 1 and 2, you could always choose, for example, being here, we could have chosen theta is equal to pi over 3 to give me a better idea. So if pi over 3 or pi over 6, let's do pi over 6. We do theta as pi over 6 is right here. Our cosine of pi over 6 is root 3 over 2. So it puts me somewhere over here, a little less than 1, but, well, you get the idea, right? We can fill in a point here to get this arc shape. Same thing here between 2 and 3. Insert another value, say pi over 3, and that's going to give you r of 1/2. So it gives you this arc shape. So the idea here is to pick a few and then insert point theta values in between if needed to fill in the missing details. So it ends up going like that. So see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Goes around twice. Goes like that. and it's on top of the previous circle-like shape here. Okay? Any question on how we did this? Okay, now let's take a look at this. It looks like a circle. Let's verify that this is indeed a circle. So we're going to transform this back into Cartesian and see if we can recognize the shape. So we're going to go from polar to Cartesian. And to do this, we're going to make use of these two fundamental identities. This is how we relate polar and Cartesian coordinates. And now you can see my equation I started with is r equal to cosine theta. I need another r on the right side to make r cosine theta. So let me multiply by r on both sides. So right-hand side is now x, right? How about left side? What's r squared in Cartesian coordinates? Right. If you add the square of these two together, right? So we see that r squared turns into x squared plus y squared. So that goes in here for the left side. Okay? Let's do a little bit more to this. I'm going to complete a square here for x, just to get a shape that we recognize. Remember, you take 1/2 of the coefficient here, square that, and add it to both sides. Then we recognize the first three as a perfect square. That's a 2. Okay, so now we see what the shape we're dealing with really is. This is a circle with a center at 1/2, 0. And a radius of 1/2, right? Okay, look at the graph we sketched on the previous slide. That's what we got. The horizontal diameter goes from 0 to 1. So the center was at 1/2, right, on that x-axis. And the radius is 1/2 because diameter is 1. So this is how we can verify that we indeed got a shape. Unfortunately, this is not something we can always do. It's not always this easy to turn a polar graph into a Cartesian graph. In fact, in general, it's not easy to recognize in Cartesian some of these shapes that we'll be dealing with. This one is kind of a special case. It's simple enough that we could do that, but usually this is not easy to do or even fruitful to attempt. All right? Okay. Okay, let's try this next one. Let's try sine of 2 theta. And we'll follow exactly the same procedure. We'll choose a bunch of theta, find the r, connect the dots. And what theta to choose? Once again, we try to find out what the period is, and then choose representative values within that period. So what's the period of sine of 2 theta, and how do you find that? Remember how to do this? Right, so what you do here is you take 2 pi divided by the coefficient of that theta. Okay? So cosine of 2 theta, sine of 2 theta, tangent of 2 theta, everything is the same way. You take 2 pi over the coefficient of theta. So this tells me my period for this graph here is pi. Then we choose a bunch of values for theta between 0 and pi, and then everything after that we know is going to repeat, right? So 0 is always a good one to start. Let's do 0. Next one, last time we chose pi over 4 because I know the value of cosine at pi over 4. Now, we're multiplying whatever theta I choose by 2. So that means when I choose theta, I should think of familiar values and divide by 2, right? So instead of pi over 4, I'm going to choose pi over 8 because 2 pi over 8 is pi over 4, and I can deal with sine of pi over 4, right? So then, just like last time, we went in intervals of pi over 4. Let's go in intervals of pi over 8. Sorry. So 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8, 5 pi over 8, 6 pi over 8, 7 pi over 8, and then pi. All right, and then this thing is going to repeat. So after this, we'll go back to here, and then come back down again. Now we deal with the values of r. Sine of 0 is 0, of course. Sine of 2 times pi over 8 is sine of pi over 4. That's root 2 over 2, roughly 0.7. And then sine of 2 times pi over 4 is sine of pi over 2. That's a 1. All right, so let's do some trig exercise here. Take 1 minute and fill in the missing values of r. Okay, that felt like 1 minute. So what goes here? Yeah. So this will take us in the second quadrant when you multiply by 2. So therefore, it's a positive sign. And this is sine of just 1 pi, which is a 0. Sine of 5 pi over 4, right? We multiply by 2 is negative. And then sine of 3 pi over 2 is negative 1. Sine of 7 pi over 4 is in the fourth quadrant. That's a negative sign. And finally, sine of 2 pi is 0. All right, there we go. Okay, you agree with these values? Yep. Okay. Then we go and graph this thing. All right. Once again, I'm going to put a few dotted lines here to kind of guide me what to do. So I wouldn't go pi over 8, because then you end up putting so many of these dotted lines, it gets confusing. Just divide the whole thing into 4 equal parts like I did here, and then fill in the missing things in between. Okay? All right, so once again, first point, theta is 0, r is 0. So we sit right here, right? Next one at pi over 8. Pi over 8 is between here and here. So let's say pi over 8 is right halfway in between. It's 0.7. Let's kind of eyeball it right here. Right? Pi over 8, theta. That's this point right here. Then pi over 4 is on the dotted line. I want to go 1 into the quadrant determined by this. So, like right here. Right? Yeah. They should. So what did I do here? Theta r. Why did I do that? Here. That'll fix it. I read theta first and then do r. That's why I wrote it. And whatever. r theta. Okay? Okay, 3 pi over 8, 1, 2, 3. 3 pi over 8 is right here. I want to go 0.7, so once again right here. And then pi over 2 puts me back here, right? All right, so let's put in this first 4 here. Kind of see this going on here, right? Then 5 pi over 8. 1, 2, 3, 4. 5 pi over 8. 5 pi over 8 puts me in the second quadrant, but with a negative r, I get kicked into the fourth quadrant. Negative 0.7, roughly here. Negative 0.7. Negative 0.7. 5 pi over 8. Right? So once again, 5 pi over 8 puts you here, but negative r kicks you into the opposite quadrant. 3 pi over 4, right here. Negative r again, so puts me right here. 7 pi over 8, right here. Gives me a negative r, so over here again. So we get this kind of shape. Right? Okay, now I need to go on to complete. I need to see my theta. I need to go all the way around. I've covered theta up to pi. I need to keep going, cover the pi to 2 pi range. But I know this thing repeats. So, for example, we're taking advantage of the period of this. So 9 pi over 8 is the next one I would choose. But I know 9 pi over 8 is the same as pi over 8. So that's 0.7. So what I can do is to use this again to count. So this is 8 pi over 8, 9 pi over 8, right here. 9 pi over 8 is right here. Has a positive r. 0.7, 9 pi over 8. And this is 10 pi over 8, which is right here. 11 pi over 8, 0.7, and 12 pi over 8, 0. Here's the next petal. Right? That 12 pi over 8? Yeah. And then 13 pi over 8, right here. But it's got a negative r, so it kicks me back to the opposite quadrant. 14 pi over 8, negative 1. 14 pi over 8, negative 1. 15 pi over 8, negative r again. And then 16 pi over 8, 0, puts me back here. Okay? So I got the first pi covered, and then I just keep counting this again, being increments of pi over 8. 8 pi over 8, 9 pi over 8, 10 pi over 8, 11 pi over 8, so on and so on and so on and so on and so on. And I can keep counting that in either direction that I want to. Okay, so we got this pretty interesting shape here. It's like a flower, right? This is actually called a rose. And this is a technical name, actually. It's a mathematical term for a shape that looks like this. We call it a rose. It's a 4-petal rose. In fact, if you sketch a few more, cosine and sine of n theta can either look like a rose or a circle. Look, we had cosine of 1 theta. We had a circle. Think of it as a rose with 1 petal. And then sine of 2 theta is a rose with 4 petals. So here is the kind of an observation we can draw, we can make after sketching a few more. So both of these will have the same general shape. R is equal to cosine n theta, and R is equal to sine n theta. Both of these will be rows with n petals if n is odd. So look at cosine of 1 theta, the first example we did. It had an odd n, so it's got that number of petals. It's a square. It's a circle, but you think of it as a flower with a square circle petal. And this is a rose with 2 n petals if n is even. Look at the second example we did. Sine of 2 theta gives me 4 petals. And actually, even with the odd number, what happens? Well, we only see n of these because 2 of them will overlap. Go back to the first example again. Notice we completed a petal at pi. But then the next one, instead of going over here, sits on top of the previous one. It's overlapping. This happens with any cosine n theta or sine n theta when n is odd. We'll have them overlapping. But with even, they don't overlap. Right? So that's the reason why we see different number of petals. Once again, even with odd, there are 2n, but we only see n of them because they overlap. Cosine petals are on the coordinate axes. So the first example we did is a cosine rose, so the petal will sit right on the coordinate axis. The second example we did is a sine rose. The petals do not sit on the axes. Okay? So we can kind of get a rough idea, even without going through all the choosing theta and all that, what this will look like. We may not be able to sketch very good representation of that, but we can at least identify what it should look like. All right, so this is going to be a rose with 8 petals. And some of these petals will sit on the axes. And the petals are evenly spaced apart. Look at the sign one. Notice the 4 petals have the same angle between all of them. So you can probably come up with a very good rough sketch of cosine of 4 theta, just knowing this, without having to go through the making a table and all that. Okay, questions? Yeah. Yes, but in that case, this is not true anymore. When n is not, that's a good question here. When n is not an integer, this is not true. Different things happen. So let me add that. That's a good point here. N is an integer. Let's do one more example. Let's try r is equal to 1 minus 3 cosine theta. All right, without this 1 minus, I know this is a rose with 1 petal, right, sitting on the axis. But when you throw this other thing in here, the shape changes dramatically. Okay, so once again, without this, we're going to get a circle. But with this, what exactly do we get? And we'll find out. So this, again, has a period of 2 pi. Therefore, my theta values should go from 0 to 2 pi. And I'll choose the same values I chose as in the first example. 0, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4. And then this will repeat after that, right? But I'm covering 2 pi already. I should be enough. These should be enough to get the complete shape. But if I want to go more, I can take advantage of that. Okay? And then we do the same thing. Plug this into here for r. So let me just fill in these values. And I'm just going to go ahead and round everything to 2 decimals. Right? So these values come from that equation. All right, so this is a very complicated shape. So I'm going to label the points again. And again, use my pi over 4 lines to guide my sketching. And here we go. Theta is 0, I'm right on here. If r is positive, I go to the right. If r is negative, I go this way. So with a negative r, negative 2, 0 theta, negative 2r. So right here. This is point number 1. Okay? Point number 2, pi over 4. Negative r puts me down here. Let's say right here. This is 2. I want 1.14, roughly half of that. Kind of eyeballing that. Pi over 2, 1. Let's see, let's do 1 here. 3. And then 3 pi over 4, 3.12, way out here. 0.4. Pi is 4. Oh, I need more room. So, oh, I got it. Let's do this. That's 1, and that's 5. And then, oh, this is, got those away. I need to kind of bring everything back, right? Oh my God, what am I doing? 4. I'm doing fine. I'm just going to have to adjust my axes a little bit. There we go. Sorry about that. But you get the idea, right? We need, just put them on here. 6, 5 pi over 4, 3.12. Right here. 7, 3 pi over 2, 1. Right here. So that's 2, that's 7. And then 7 pi over 4 puts me negative again. 8. And then 9, 2 pi, negative 2. All right, so when I send the notes out today, I'll do a better sketch this, okay? I'll fix this after class. Okay, so what we end up getting, this is a very strange shape. Let me sketch it out first, and then we'll talk about it. Oh man. Okay, so let me fix this better here. It should look something like this. It's a circle within, kind of like a circle within a circle. Again, I'll fix this when I send the notes out today. Sorry about this thing here. But the idea, you get the idea. You put these points here and just follow the order. This kind of shape has a French name. It's called a limaçon. If you know French, this is one of the French letters, a C with a little tail at the bottom. But if you don't know French, it's a funny-looking C. That you treat it like an S, basically. This is called a limaçon. What limaçon means is snail. So, you know, you can, I guess if you have some imagination, you kind of see a snail out of this thing. But that's the kind of shape we get. Okay, that's it. See you Wednesday.